This is Mr. Marcotte. I'm here recording this for you from my home. Um, and we're just going to go over a few real basic, um, simple introductory definitions here. If you don't have your book, that's okay. You don't have to take notes in your book for this section, although these things are found in your book, and you may find it helpful to annotate. Um, but we'll be in section 1.1. But there are just some real basic definitions we need to go over. The first of which is a point. So a point is any specific location in either space or in some two-dimensional area. Um, and we represent that point with a dot. So we draw a dot. So I'll do one down here. I'll draw this little point. I'll call this point A. I prefer to go alphabetical usually. So here's point A. It's labeled. My favorite trick question is to ask somebody, okay, well, how wide is point A? And usually what they do is they're like, oh, look at this, I know how to use a ruler, hooray! And they grab their ruler, and we'll use centimeters here, and they'll come up and they'll say, oh, point A is, you know, 0.4 centimeters wide. Like, no, wrong. Look up here. It says it has no dimension. If something has no dimensions, it has no length or width. Um, it cannot be, this dot may be zero point 0.4 centimeters wide because if it had no dimensions, we won't be able to see it. But the point itself actually has no dimensions. It is merely a single location, right? So it's a little weird. You have to get your mind past the fact that um, these are pictures that represent these geographic terms that are purely conceptual. Um, and it's important to have the concept of a point, right? If I were to do a point to point here, like let's say I want to get from point A to point B, and I again want to measure that distance, I wouldn't just say, oh, you know, from the edge of this one to the edge of that one. No, no, no. Well, we're talking about like wherever point A is, which would probably be at the center of that dot or something like that. You know, we can't see an infinitesimally small point, so we just represent them using dots. Similarly, lines. Lines, in a similar way, have no dimension, but in one particular way they have a dimension. Um, well, okay, they don't have dimensions, but lines are basically um, an infinite number of points that go in a straight path. We use the term line like, oh, hey, look at this, I drew a line on a paper. Here in geometry class, this is not a line. Lines are always perfectly straight. So just keep that in mind. That means any 2 points you may have. So here's any 2 points. There's exactly one line that connects these 2 points, right? Zoom, zoom, zoom. And lines are infinite. We can't draw an infinite line. Similarly, there is no thickness, right? Here on my computer, whenever I use any tool that draws, it has some kind of thickness. But true lines have no thickness. They're simply uh, they're simply a series of points that go in a straight path, an infinite number of points in a straight path, right? So again, start thinking of these things as conceptual. They also go on forever. So this guy goes on forever in this direction and forever in this direction. I can't draw forever, right? So in one way, it's infinitesimal, right? There's no width to a line. So we have to break that a little bit by drawing thickness so we can see it. In the other direction, it's infinite, and I can't draw infinity, so we're going to cheat a little bit and just say, oh, hey, look at this. There, we'll draw some arrows on the end, and those arrows mean that it's going to go on essentially forever in both directions. So that's what these arrows here are, and they can label it that way. Ways to name them, we can pick any 2 points on that line, and we can just use that as the name. So we can say line AB. You can also draw an A and a B and then put the basically a little line symbol over it. BA doesn't matter. Direction doesn't matter in those cases. Finally, a plane. So this one's probably the hardest one to visualize because it's really, really hard to draw. I'm not even going to attempt it. I'll just use theirs. But essentially what they're doing is they're using like a flat sheet of paper. It's not flat. It's flat-ish. So you take like a plane kind of represents, or a flat sheet of paper kind of represents a plane in that it's, very thin. Real planes have no thickness, right? In this case, instead of ending, right, just like our line, we can't draw the line forever. Planes we can't draw forever. So planes extend in all directions in an infinite way. And that's what this little parallelogram is trying to represent. It's kind of like a sheet of paper. So this is called plane R, and it can be defined by any 3 points in the plane. Once you have 3 points, you've defined a plane. So they call this plane XYZ because they're point X, point Y, and point Z are in that plane. Note here that we have to make a few assumptions just based on the figure. We have to assume that this, they can tell us that it's plane R, right? But just by looking at it, we kind of have to assume that point X is here in the plane, and point Y and point Z. They would have to indicate that it's not in the plane by doing something to just make that clear. So even though we're dealing with these figures that are trying to visualize these abstract things that don't really exist, we still need to make a few little assumptions about the figures. And be careful, we'll get into more complex figures, and it's really tempting to make all these assumptions, be like, oh, hey, look at this. Here's a triangle, and that's a right triangle because that's a right angle. Nowhere does it say that that's a right angle, so we can't assume that. There'll be many examples like that. So be super careful making assumptions. But one assumption we can make is there's a point, it looks like it's in a plane, it will be in a plane unless otherwise specified. Okay, 2 more easy ones. Line segment. A segment is basically any portion of a line. So in this case, it has it's any portion of a line between 2 points. So in this case, we have CD, which is simply, a straight infinite numbers of points here that connect C to D. So again, segments are straight, and they connect things. We can write those as segment CD, or you can write CD with a little single. My segment symbol here, again, doesn't have the arrows because segments aren't infinite. They don't go infinite in both directions. So notice the symbol here has no little arrows. And again, the order doesn't matter. CD is the same thing as DC. They're the same segment. The one where order does matter, as it turns out, is ray. So a ray is kind of in between a segment and a line. It looks like a segment over at this end because it stops, it doesn't go any further. But then on the other end, it goes forever. It goes pa-choo, and it just keeps on going and going and going. So I could have drawn this ray, much longer or much shorter. So for these guys, we need to specify which one is the finite end, and we do that with the first letter. So if you say ray PQ, it means it starts at P and goes through Q and goes on for infinity. Or you can draw it with this little ray symbol above the top. So those are our 5 definitions. One last thing to point out is that you're going to run across a couple of these sorts of things in the book. There are going to be postulates or theorems or some kind of thing that we need to pay attention to. And they come in these little boxes. A postulate is essentially a conclusion or fact that's been, in this case, proposed by the book. And we'll go through and we can essentially prove this later. But for now, we'll just take postulates as true or at face value. So in this case, postulate 1 is the segment addition postulate. And our accepted fact here is if you have A, B, and C as collinear points, right? Collinear meaning they're all on the same line. And point B is between A and C, then essentially you can say that segment AB plus segment BC is equal to AC. I was building a bookcase, and you'd use a ruler and do really simple things like this, right? So I'd have this piece of wood, which is, say, 8 inches long, and I'd have this piece of wood, which is 4 inches long, and I put them both together so they make a nice straight line. How many inches long is this whole deal? Well, it's 12 inches. This seems super basic and might be beneath you, but we need a reason to be able to say that these two added together is equal to this. In addition, note here that some people may, if it's not collinear, some people may try to add them together or do something silly like that. So we just need to be clear about that. Another assumption we can make about figures is that if things look collinear, they are collinear. Or in other words, if you see something that looks like a straight line, it is a straight line unless otherwise shown. So this looks kind of like a straight line, A, B, C. Some people may try to get super pedantic on you and be like, oh, maybe that's, instead of being 180 degrees, maybe it's 180.001 degrees. Okay, sure. Yes, but that's why we have to, do some reasonable assumptions here. And one reasonable assumption is that there's a straight line, therefore it's 180 degrees. Okay, that's it for this video. Check out the other one if you want to do the second part of 1.1.